In the name of Almighty God, I am Master Sankoshi, and today I want to talk about acoustic structure. Actually, acoustic relates to sound or hearing and can also refer to a musical instrument that produces sound naturally without electronic amplification. It is also used in the context of the science of sound acoustic and the properties of a specific space that affect sound quality. Acoustics are relating to sound. Science of sound, the study of sound's production, transmission, and effect is known as acoustic. The next one is sound related materials. Materials designed to control or absorb sound are called acoustic. The next one is sound waves. It can describe something that is operated by or uses sound waves. The next one is medical. It can refer to the sense of hearing or the organs involved. And what is about acoustic in music? The first one is instrument, refers to a musical instrument that is played without electronic enhancement such as an acoustic guitar. The next one is performance. An acoustic performance uses only non-electric instruments. Acoustic in a building or room. Room quality. It refers to how a building or room's structure affects the quality of sound within it. The next one is acoustic design. This is the practice of designing a space to control how sound behaves within it. And now I want to talk about acoustic structure interaction, which is a phenomenon where acoustic pressure waves in a fluid affect the vibration of a solid structure, and the structure's vibration in turn generates new pressure waves in the fluid. This multiphysics coupling is essential for modeling and designing a wide range of products, from vehicles to loudspeakers, to optimize sound generation, transmission, and absorption. Key principles involve ensuring the normal perpendicular particle velocity is identical at the fluid-solid boundary, a condition that links the equations governing both the fluid and the structures. And what are the key principles? The first one is coupled physics. Acoustic structural interaction involves two distinct physical phenomena. The first one is acoustics, medium pressure waves in a fluid, and the next one is structural mechanics, vibrations in a solid. The next concept is boundary conditions. At the interface where the fluid and solid meet, the coupling is defined by a no-slip condition for the normal velocity. This means the component of the structure's vibration perpendicular to the boundary is the same as the particle velocity of the fluid at the same point. The next context is the bilateral effect. The interaction is reciprocal. Pressure from the fluid causes the structure to vibrate, and the structure's vibration creates new pressure waves in the fluid. The next chapter is modeling. The behavior is just predicted by solving coupled equations for both the fluid and solid domains. This requires a specialized software that can handle multiphysics simulations to account for the interaction at the boundary. And what are the applications? The first one is noise reduction. In automotive and construction industries, acoustic structure interaction is used to design parts that minimize unwanted noise by optimizing their shape and material properties to absorb or reflect sound. The next one is sound generation. It is fundamental to design of devices that create sound, such as loudspeakers and musical instruments. The next one is structural integrity. Acoustic structural interaction is used to understand how acoustic forces can cause structural failures, such as in the interaction between a dam and a reservoir of water. The next one is medical devices. It is applied to acoustic devices like earphone to optimize their performance and prevent damage from acoustic waves. FSA, or fluid structural interaction analysis, refer to a method used to evaluate the dynamic characteristics of a structure in relation to the surrounding fluid, particularly in terms of how fluid properties affect resonance frequencies and other performance metrics. This analysis can determine fluid pressure and velocity, which serve as a boundary conditions for further studies on the droplet characteristics and acoustic pressure waves. This model provides a simulation on modeling the interaction of sound with elastic solid structures by using a specific example of an elastic cylinder in water. The sound will cause movement of the solid cylinder, which in turn will induce new sound waves in the air. Thus, full two-way coupling between the acoustic medium, which means water, and the cylinder is required to realistically simulate the situation. This model is similar to the interaction of acoustic signals or sound with most everyday objects. Liquid or gas acoustics coupled to structural objects have applications in many engineering fields, for example, loudspeakers, acoustic sensors, non-destructive impedance testing, medical ultrasound diagnostic of the human body. The intent within this intuitorial model is to illustrate the modeling process rather than to provide an exhaustive illustration of the acoustic solid interaction capabilities of COMSOL. This model requires both the acoustic model and the solid mechanic module. Model definition. This model simulates the behavior of a solid cylinder in the water domain with an incident acoustic wave in the water. The object's wall are impacted by the acoustic pressure. The model calculates the frequency response from the solid and then feeds this information back to the acoustic domain so that it can analyze the resulting wave pattern. As such, the model is a good example of a scattering acoustic solid interaction problem. Acoustic electricity from the ocean can refer to two different concepts. The first one is generating electricity from ocean sound waves, and the next one is harnessing the acoustic energy of ocean waves themselves. The first one involves using sound waves to enhance the power output of surface waves through a phenomenon called triode resonance, while the second one uses devices to convert the mechanical energy of ocean waves into electricity, harnessing acoustic energy from the ocean waves. The first concept is ocean waves as an energy source. The ocean has immense potential for renewable energy, with its waves holding an estimated 2 to 3 times the world's annual energy consumption. And how it works. Ocean waves are converted into electricity using wave energy converters. These devices capture the kinetic and potential energy of waves and convert it into electricity through various mechanisms. An example of wave energy converters. A common type of wave energy converter is a floating buoy that moves up and down with waves. This vertical motion derives a generator, often through a rack and a pinion mechanism, to produce electricity. And what are the challenges? The primary challenge is developing efficient and durable technology that can withstand the harsh ocean environment, using acoustic waves to enhance wave energy generation. And what about triode resonance? Research is exploring how to use underwater acoustic sound waves to amplify surface waves and how it works. Underwater acoustic waves generated by events like earthquakes or volcanoes can interact with the surface waves through a phenomenon called triode resonance. In this process, two acoustic waves transfer energy to a surface wave, increasing the surface wave's amplitude and power. And what about potential application? By using an acoustic wave generator tuned to specific frequencies, it may be possible to intentionally amplify surface waves and improve the efficiency of wave energy converters. And other acoustic phenomena in the ocean. The first one is ocean microbarometer. Colliding sea surface waves can generate an acoustic signal called the ocean microbarometer, which can transmit significant energy to the upper atmosphere. This is a natural phenomenon, and while it involves acoustic waves, it is not a method for generating usable electricity. Measuring live sounds. The ocean contains acoustic energy from the various sources, including marine animals. However, this is a different phenomenon and is not related to electricity generation. Wave energy's huge potential could finally be unlocked by the power of sound. Ocean waves have long been seen as having huge potential as a source of renewable energy. Waves produce an estimated 50 trillion to 80 trillion watts of power worldwide, nearly 2 to 3 times the world's current annual energy consumption. Many devices have been designed to capture and convert waves' great power into electricity, but today's technology faces challenges in efficiency, particularly in deeper water. As a result, wave energy hasn't yet taken off as a renewable source in the same way as wind and solar system. One way around this problem lies in the interaction between two types of wave, those on the ocean surface and those that reside underwater. My research group has just published a paper demonstrating how underwater sound waves can be used to make surface waves more powerful, potentially making them a more viable source of energy. The same insights could also eventually be used to reduce the risks of tsunami by making them smaller. In addition, in a second new paper, we should show how underwater waves can be used to improve today's tsunami early warning system. The waves on the surface of the ocean are often created by a combination of wind raising up water and gravity pulling it back down. Hence, they are sometimes referred to as surface gravity waves. On the other hand, their underwater counterparts are sound waves produced by phenomena like earthquakes or volcanic eruptions, sometimes thousands of meters below the surface. These acoustic waves travel by compressing and expanding the water, similar to how sound moves through the air. They travel across transoceanic distances at the speed of sound in water, around 1,500 meters per second, before eventually dissipation. Surface waves travel at much lower speed, in the order of tens of meters per second. In classical water waves theory, these two types of waves are considered separated entities, each living in its own world at its own rate. The possibility of them increasing only arose on the back of a 2013 research which promoted a phenomenon known as triad resonance. This is where two acoustic waves transfer energy to a surface wave by matching its frequency, which in turn causes the surface wave to get larger and more powerful by increasing its amplitude. This opens up the possibility of using an acoustic wave generator to generate sound waves tuned to a particular size and frequency that would enhance or equally suppress surface waves. Enhanced waves would enable today's wave turbines and oscillating water columns, which use wave power to force air through a turbine to produce more electricity effectively, overcoming their efficiency problem. Acoustic wave could enhance the power of surface waves. Wonderful nature. The main requirement would be an acoustic wave generator that could be finely tuned at the required scale. Acoustic wave generators already exist for laboratory purpose, so it's a question of scaling up an existing technology. Our research findings show that triad resonance can increase surface wave heights by more than 30%. Of course, the generator would require energy through the hope is that this too could be powered by waves to minimize carbon emissions. One additional challenge is to ensure that methods are developed to use the acoustic energy efficiency to ensure that the least possible energy is wasted. Our next step is to produce some more numerical simulations and to conduct a series of small-scale laboratory experiments looking at how triad resonance works in practice. This will help refine our theories and assess their feasibility, hopefully with a view to tuning this into a commercial reality. Tsunami mitigation. I originally suggested the possibility of reducing the height of tsunami waves by manipulating underwater acoustic waves back in 2017. In the new paper, we look at this in more detail. We found that the resonance mechanism certainly took place at the oceanic scale during the 2022 Tonga earthquake and tsunami. This shows that it's theoretically possible to manipulate the size of tsunami using other techniques. A volcano eruption in the Tonga archipelago in January 2022 triggered a tsunami that swallowed an island. Zoomaperis, the challenge lies in generating and directing the acoustic waves at the required scale and configuration in real-world conditions. This would be more challenging than using acoustic waves to help harness wave energy, not least because of the scale of tsunami, which would necessitate a much more powerful acoustic wave generator. Other issues to overcome would be knowing the exact properties of the tsunami in real time, and the risk that using the wrong configurations could actually make the wave bigger instead of smaller. While it could take some time to make this feasible, acoustic waves can also potentially help to mitigate tsunami in a different way. Our second paper demonstrates that monitoring and analyzing these waves in real time could complement the existing and emerging technologies for predicting tsunamis, including ocean buoys and seismometers. There are currently thousands of seismometers deployed around the world, but they only monitor earthquakes, whereas tsunamis can also be caused by landslide explosions and volcanic eruption, even with earthquakes. Large seismic readings don't always entail large tsunamis. This can lead to false alarms, such as in Alaska in 2018. Meanwhile, ocean buoys, which measure sea levels and water pressure, are often faulty because of their operating conditions and also relatively slow at giving warning when tsunami, according to my calculation, can move at speed of up to 200 meters per second in the deep ocean. A complementary system is to measure acoustic waves using an underwater microphone known as a hydrophone. These capture the acoustic waves created by all of the phenomena that cause tsunami, and the speed at which these waves travel means that just 30 hydrophone situations could cover the entire world tsunami high-risk areas. This could be particularly life-saving for coastal communities near the source of a tsunami. It would also support global goals for more resilient coastal cities, such as UNESCO aims to make all such places tsunami-ready by 2030. Liquid or gas acoustics couped to a structural objects such as membranes, plates, or solids are important applications in many engineering fields. This model is general demonstration of an acoustic fluid phenomena in three-dimensional that is cooked to a solid object. The walls of the solid object are impacted by the acoustic pressure. The frequency response from the solid is calculated, which is then fed back to the acoustic domain so that the wave pattern can be analyzed. As such, the model becomes a good example of a scattering problem. Thank you so much for watching my tutorial video until the end. And here there is my simulation acoustic structure that you can see that I have used both pressure acoustic frequency domain and solid mechanics as a physical module, and the study type is for a sound hard sealant and aluminum sealant, and you can see that we have a wave and medium, and there is a structural solid that the wave will be scattered through it. And here you can see that in the water, the ionization from the anode to the cathode, and I will talk about it in the next simulation more. And here you can see the results. There is sound pressure level along propagation domain between the hard cylinder and aluminum cylinder, and the wave that has been scattered through them.